I would like to tell you a bit more about the origin and the diagnostics of familial breast cancer. Let me first start and introduce breast cancer as a most frequent cancer in women. About 1 in 10 women will eventually get breast cancer. This is a cumulative disease or a cumulative risk in a sense that this 1 in 10 is true by the age of when the women will get about 80 years old. But even at 50, 55 years of age, the incidence of breast cancer becomes important. Breast cancer is about 10 times more frequent than ovarian cancer, but the problem with ovarian cancer is that it's more dramatic and that it's because it's more aggressive as a cancer. So there is more deaths from ovarian cancer than there is from breast cancer. Now you should remember that most cancers are sporadic. It means they occur as multifactorial diseases and no one can predict who will get cancer, when and why. But in some cases, one sees that these cancers cluster in families. So it means that in a family you have more than one woman who is affected with breast cancer or ovarian cancer. And this is what we call the familial cases. This is what we call a familial cancer syndrome. The basis for this cancer in the families is not that one inherits a cancer, because one cannot inherit a cancer, but what one can inherit is a susceptibility to develop the cancer. And that susceptibility is autosomal dominant, so it goes from one generation to the next with a risk of 50% for each person in each generation. About 20 years ago, people have identified 2 genes that are very important for breast cancer. It's the BRCA1 gene and the BRCA2 gene. These are 2 genes that are tumor suppressor genes, and this tumor suppressor paradigm explains why one can inherit breast cancer as a susceptibility, because they will need a second hit to cause the disease. And the second hit would occur in any breast cell and thus cause cancer. It's 2 relatively big genes, so if one would like to sequence both genes in all patients, it would be really expensive. So that's why eventually we need guidelines to select the families. Now just to take you back to the frequency of this breast cancer, as I mentioned, the normal population has a risk of 1 in 10 by the age of 80 or 85. In cancer families, we see that this risk is elevated to 80%. So it means that someone who is a carrier of a BRCA1 or BRCA2 mutation has an 80% lifetime risk of developing cancer. And if you look at the figure at about 45 years of age, already 30% of the women will develop breast cancer at that age. So it means it's really a burden on those families and it's a high risk. That's why we call it high-risk families. Now, as I said, it's quite expensive to look at both genes at the same time in all patients, because there's lots of patients, and if we would sequence all the patients, we would only have like 1 or 2% of positive cases, because that's the frequency of BRCA1 or BRCA2 mutations. So that's why in practice, we tend to select the families, because if you can select the very high-risk families, then you can get up to 25% of BRCA1 mutations and up to 15% of BRCA2 mutations. So the practical approach in most countries is that the families are selected first before molecular testing is being offered. And one of the criteria, which is the most important criterion, is that one needs 3 affected family members. We don't distinguish between breast cancer and ovarian cancer. We don't see a difference. So 3 family members with the disease are sufficient to say this is a high-risk family. Of course, one needs an extended family. If the family is too small, this criterion cannot apply. We would also take families with male breast cancer. Males can also get breast cancer. It's far less frequent, but it happens more frequently in familial cancer families. So we would include those families as well. we would include patients that develop breast cancer at a very young age, and keep in mind this tumor suppressor model where one hit is sufficient, so if it occurs, it may occur at an early age. And we would also include special types of breast cancer, which are, for instance, the triple-negative breast cancer, because we know that there the frequency of the mutations is elevated as well. And recently we've also decided to include all the ovarian cancer, because there is a therapy for BRCA1 and BRCA2 mutations in ovarian cancer. All analysis would always start from an affected family member. It doesn't make sense to check a non-affected family member, because you have the a priori chance that she doesn't have the familial mutation in 50% of the cases. So this is a typical pedigree where we have this unaffected woman who is seeking advice because in her family she has breast cancer or ovarian cancer, and recently her cousin developed breast cancer. So she gets uneasy, she knows that the cancer has reached her generation and she wants advice. Well, we will tell her first that she has to make sure that the other family members come in and have their blood samples taken, because we want to start from a familial breast cancer case. So we will always start from a affected family member to do the analysis. The prime example, of course, everybody knows her, is Angelina Jolie, who was at risk for breast cancer because of a breast cancer mutation in her mother. She took the test, was positive, and had preventive measures taken. In her case, she opted for a mastectomy, and then later her ovarium was removed as well. So what do we see as a result of this predictive testing? Because we have selected the families, about 9 to 12% of the families are positive, meaning that we can find a BRCA1 or BRCA2 mutation. And in these families, like in Angelina Jolie's families, predictive testing now becomes possible. Because we know the familial mutation, we can check specifically for that mutation and see whether or not the daughter has inherited the mutation. And as I said, Angelina Jolie had bad luck and inherited the familial mutation, because a priori she would have a 50% chance of escaping from that familial trait. If the mutation is found, it is important to realize that these people now enter in the high-risk category, meaning that they have 80% chance of developing breast cancer, 20% chance of developing ovarian cancer. If the mutation analysis is negative in that woman, it means she has not inherited the familial mutation and she will have only the normal population risk. Her risk will not be 0, her risk will be back to 10%. If there is no mutation found in the family, which is the case in 90% of the families, there's nothing we can offer at the individual's level. We can only use empirical data to predict a relative risk for the women to develop the cancer. Now I'm coming back to this slide. The question is, what is then the other cause of disease? We only see breast cancer 1 and breast cancer 2 in about maximally 40% of the cases. What is the other cause of breast cancer? And not much is known there. On the one hand, we have a few genes that cause have very small contributions to familial breast cancer, and one of them is the high-risk gene called TP53, which one may know from the Li-Fraumeni syndrome. And then we have a number of genes which are moderate risk genes, like ATM, like CHEK2, and then a whole series of rare gene defects that we see in familial cases. But they altogether only account for about 3 to 5% of all the familial breast cases. So in the other group of the diseases, we have no idea what is causing the disease. And probably these are constellations of low-risk alleles, which means more common alleles common in the population that confer a risk for sporadic breast cancer, and that if the risk is increased, you see these sporadic cancers cluster in families. So this is a schematic representation of the high risk but low frequency variants with BRCA1, BRCA2, and then the common variants with a relatively low risk but a high frequency in the normal population. Now, the question is, as usual, what about the treatment of these familial cancers? Well, the good news is that there is one drug that specifically addresses BRCA1 and BRCA2 cases. And because if we want to understand why, we need to know about the cell biology of breast cancer 1 and breast cancer 2. These proteins are involved in DNA repair. So we can easily link DNA repair to tumor development. If there is no DNA repair, a tumor will develop much faster than if the DNA repair is in order. And more specifically, BRCA1 and BRCA2 are involved in what one calls the repair of double-strand breaks. So it's called non-homologous chromosomal corrections or chromosomal repair, because the proteins are necessary to just repair a chromosome that is broken. And if you can't repair your broken chromosomes, eventually you will get a tumor. Now, it's important to know that that tumor itself has to survive, because if there's too many errors in the tumor cell will also die, and then you don't have a tumor. And for doing that, the tumor is depending on other pathways, which are also pathways of DNA repair, but they are less specific. And one of them is called the PARP pathway. And what is PARP doing? PARP is repairing, but not by homologous recombination, but by non-homologous recombination. So it's a bit more sloppy, but the tumor cell can use it to survive. Now, the idea is if we can interfere with that second pathway, with that PARP inhibition pathway, and turn it down in the tumor cell will eventually die. Whereas, why does it not affect the normal tissue? Well, the normal tissue has still the BRCA1 repair system or the BRCA2 repair system. So these systems are intact unless the tumor suppressor gene is lost. So in the normal tissue, the PARP inhibition will not interfere with survival, but in the tumor, it will kill the tumor and thus be a drug for familial breast cancer.